Good evening, everybody. Hey, it's great to see so many folks. I want everybody in here to wave at Joe Boyd.
Hey, Joe. Hey, Joe.
There we go. He can see you. He's waving back. He's our, lone right now anyway, person on Zoom. But Joe, for those of you that don't know him, has been a member here forever. Past president, just, anyway, we're happy to have
so much.
Oh, all right. So we're going to call to order our regular meeting. I'm going to try to run through this fairly quickly. So hopefully everybody read the minutes in the Eclipse. It's okay if you didn't, but if you did, hopefully nobody found any egregious errors. And do read them, because sometimes there's fun things, and if you missed a meeting or two, you might have questions about, hey, what's coming up or what's going on. So give them a look. Keith is not online with us, so I don't know rightly how many members we have. I think it's in the 150 range right now. Oh, wait, I have some numbers here. I should look at the presenter view. As of, it looks like 165, so that's cool. Keith will eventually, if you don't pay the yearly dues, he'll eventually get around to sending you an email. So, I probably should have given treasurer's report. We do have a little bit of money. We've got almost $6,000 in the bank at the moment, which is kind of split between an equipment fund and the checking account. We had a couple of big purchases right at the end of the year, one of which is a pile of solar glasses, because you got to buy them now. You can't buy them when everybody wants them. So if you want them as a member, it is a perk of membership. You get 2 free pair. If you want more, I will sell them to you for $1 a pair. If you have an organization like a school, especially, that needs a whole lot, ask me, because we will make them a deal, because students should have solar glasses and be out looking at the eclipse. That's just something I feel real strongly about. So we ordered enough that we got a really, really good price. So for big groups, I would totally pass that along. All right.
Did you bring them tonight? Or?
I brought some tonight. So okay. Yes, I do have some. And for those of you who ordered a handbook, I have those as well. So see me before you leave to pick up your copy, and we will get that so we can move those out the door. The rest of them I will mail out as the week goes on and I get some time, but that's really good. Let's see what other interesting things. There are 2 posters over here that suffered some water damage, and so you can bid on those if you want a pristine copy. I actually have 2 nice ones over here. I kind of think you might not notice the water stain. It kind of blends in with the rest of the coloring on the poster, but anyway. And again, feel free to browse the table and check stuff out over there. Let's see. I think that's really about it. We're looking forward to next year. I do have a list, and we'll be posting it as soon as we can, of what the Star Party dates are. Bowie Park I talked to today, and they just got a new program manager, so she was super excited, to have some dates out there, and promises that they will actually start promoting them, and she'll be there when we have them. So that was really nice. All right, and Steve and I are going to be at Warner Park tomorrow. They're doing a solstice celebration from 4 to 7. If anybody wants to drop by, that'd be fun. We were going to set up telescopes. It doesn't look like the weather is going to accommodate us, so we might be in their classroom. I know Steve put some pictures up. I put some pictures up. I think there's a couple from some other people there too. They wanted to decorate the classroom at Warner Park with pictures of the night sky. And so there's some really cool pictures. So if you want to come by tomorrow sometime, that would be a fun thing.
That's at the Nature Center?
Yep. Yep.
You're going to make a little thing on that. So there's a couple people I talked to here. So I'll have my astrophotography rig there if anybody, I know it's real super last minute, but I'll have my rig there. So if anybody wants to come by and see it, it'll be indoors. Yeah. And I'll be doing some demonstrations for the public and stuff. 4 to 7 o'clock tomorrow.
So that's good fun. All right, so there is equipment available, whoops, for loan. Oh, come on. What did I do? Get past too many of them the first time? Okay, there we go. There is a list, it's somewhere on the Google group. We should probably just repost it every 6 months so it flies to the top of the list. I know I've got a couple pieces at the house, including if you don't win this cute little ETX over here, the club does have one too. So, or we might end up with two, although I think Tom was looking at that. That's because they're cute and they're small and they're easy to take with you places. So that's what's nice about those. So anyway, let us know if we can help you out with equipment, with trying something out. We've got a couple of good sized dogs and a couple of other equipment, some of which I would call almost antique, but that's fun to use too.
And solar stuff too.
Yep. Solar stuff is really good. The sun is actually looking cool now instead of blank and dull like it was for a long time. All right, so we are going to start meeting. This is our last meeting here. We're going to start meeting at Dyer Observatory. That's kind of a full circle thing for us. The club used to meet there and now we're going back. Both of our names, Barnard and Seifert, both are Vandy people. So it's kind of cool that we're kind of going back to our roots there. So this will be a lot of fun. And Dr. Billy says he will join us for our talks. So that'll be good too.
There's something about an event in July 17.
So that's the
Why
one
is
that
that
we
noted?
can't, normally we meet on the third Wednesday, but that Wednesday he's got camp. So we're gonna bump down a week on that for that month. And we'll try to make sure that everybody knows that, because that's kind of, you know, when you do
Okay.
something regular and then you have a change, that's always a problem, but
If you show up there and it's all 8-year-olds,
yeah.
You're in the wrong.
It's the wrong thing. Yeah. Although you might get drafted to help with the 8-year-olds.
Theo, is there any discussion with Billy about having a viewing on our meeting nights?
Not yet. I should have said something to him when I was there this week, but you know, that's one of those things that if he thought, if it was a nice night, maybe you could talk him into it. Because he likes to show off the scope too. But yeah, we'll have to talk about that. But then we'll have to not run over, right? We'll have to, you know, leave time for that. All right. We have a great website. Every social media site we have is bsasnashville.com, so you don't have to think too hard about it. But the website generally has the public star party that's coming up, so I need to change this. We got canceled out last week. The next meeting, and then the next after that public star party. So there's our lovely hatch print. There's an ad for the solar glasses that links to where you can get them. And of course, the clear sky chart too. So yeah, get your safe solar glasses. Get them now before they're all gone. This is not cheap stuff from China.
You said you wanted club members to be selling the solar lights.
I mean, if you've got an office or something and you want to walk around, we did this with our kids shamelessly before the last one, where we had them go around their dad's office and just say, hey, you know, $2 a piece or whatever. And they sold a lot of glasses that way. And yeah, why not? You support your local club and you get safe solar glasses. Cool. And what is that? Is that our, yeah, that's our Facebook page, which is also bsasnashville.com. X, formerly known as Twitter. So, which, I mean, I just post, you know, I'll repost things that I think are interesting. I'm real bad though. I'm not a child of social media. So, you know, I have to have the time and inclination to go there and look at it. So sometimes time passes, especially for Facebook, but Chip is doing some of it too. And that's a huge help. But if anybody else wants to help with posting events and publicizing, please let us know. Something else that would be fun to do, Drew has been doing the newsletter for like a decade. I used to work with Drew at the planetarium. He's a great guy, but 10 years is a long time to do anything. So if anybody else has skills of putting together a newsletter once a month and would like to have a crack at it, Drew would love to hand it off to you. And Instagram, which Steve Hughes, where's there, Steve, is taken care of for us, which is great. Because I don't do that at all. There we go, winter solstice celebration. And we do a number of daytime events sometimes at the parks. If they, have something coming up, we'll have a daytime table. Maybe we can look at the sun, maybe not, but we can always talk to people and tell them what we do and encourage people to turn off their darn lights at night. The Night Sky Network, which is where we keep all of our membership information. And I have trouble, like I just said, yeah, you can go check your stuff on there. But if I look at it, I'm looking at it as an administrator, so I can't look at it in the same way you can. So, but I think you can go in and check when the last time you paid is. But the Night Sky Network itself has some really fun things. If you're looking for an activity to do with a group, it is a great place to find some activities. Lots of outreach resources, lots of, what's going on in the sky this month. There's a lot of good stuff there. So let's see, this is what we've been doing. And that was not at Bell's Bend, that was at Shelby, but that's okay. It was canceled anyway.
So was somebody at Natchez Trace?
I don't know. I don't do those. Is anybody here that does those, goes out to the Natchez Trace dark sky sites? Oh, sad. So we don't know. We have a permit to use 2 pull-offs along the Natchez Trace. The trace is technically closed at night. How do you close a road? I know, but the rangers do patrol it. And so we have a permit to use 2 pull-offs once a month. And so if you do go out there or you want to go out there, that's when you use the Google group to find out and to connect with somebody else that might go out there, because it's a really lonely place otherwise. There's no facilities out there, and we have a member that lives within shouting distance of the Water Valley Overlook one, who occasionally will say, why don't you just come to my house? I have heat, I have a bathroom. And so sometimes people are meeting at his house. On the 10th, yeah. Yeah, that was not a good week to be outside, so probably nobody was there. The January meeting is our annual telescope workshop. We actually will encourage members of the public from our Facebook group and that if you have a telescope that you got for Christmas and you can't make it work, bring it out, we will make it work. Which of course means we'll read the instruction manual, right? But there, a lot of time it's really simple stuff, and the manuals assume that you know things that you might or might not know. They use words that don't mean the same things to a lot of people, so it's useful to have people bring their gear, put it down, and we'll go through it with them.
What kind of turnout did you get from the public?
There were times when we had a lot of people. We'd have 10 or 15 people bring gear, and we'd set it up. And usually what I do, I tell them too, if you have, like I have a really classic Newtonian that I bring to star parties. You can come and look at mine. It's going to work exactly like yours. So I'll set that up, bring one of the club Dobbs. If you have a Dobb, here's, and you can just look at what we've got and here's how you work it. So, COVID put a big hole in stuff like that and we got out of the habit of doing those sorts of things. So maybe saying, hey, we're doing this cool thing and it's at Dyer, which is extra cool. Maybe that will help. And then our first public star party of the month. It's nice that this year, some years it's come right at the front of the month, which is still cold and yucky. And maybe by January 20th, it'll be a nice night. So that's at Warner Park. Sunset's right around 5, so we'll start around 6. That's always a balance of wanting to come while it's still a little light to set up and not standing around for too long, you know, it being dark. So we'll start early and end early, but we usually have a good turnout at Warner Park. So that's what we've got. And then Saturday, the 13th is the private star party. I guess the permit is still pending. We haven't gotten it back from them yet. It's the federal government. You fill out the paperwork, you send it to them, time passes, so. But we've had a permit to do that for 20 years, maybe more. All right. Coming up, we're pretty done with December. Yeah, the Ursa meteor shower. Okay. The Geminids were pretty good. How many people saw a Geminid meteor? Yeah, they were actually pretty good this year, I thought. So that was nice. Then we have a few other things. There are a few that aren't listed here. Right at the end of December, there's a double shadow transit on Jupiter. That's kind of in the early evening. That's what the Observer's Handbook is great for. You page to the December, you know, page and you see, oh, that's a cool thing. If you've never seen one of those, the moons will throw a shadow on Jupiter.
Right.
And you can see that. It's just the coolest little inky brown shadow. So those are really fun and interesting to see.
When you say no transit, are they both shadows on at the same time?
Yes.
Just two in the night.
Yep. So they'll both go across. And sometimes, like, there was one in October that I was fortunate enough to see, Ganymede, and what the angle it was making, it was just skimming. The moon itself was in the frame the whole time, just skimming the top of Jupiter, and you could watch the shadow and the moon going across the way. So it's kind of fun. So that's an interesting thing. But yeah, Mercury at greatest eastern elongation, boy. Mercury is fun if you've never seen it, which a lot of people actually haven't because it's hard. Wait for it to be in the evening sky at its greatest elongation there. And then you just have to have a stinking clear night because it's always low, always in the sunset sky, and it's not that bright. It's not like Venus, right? If you walk out right now into the early morning sky, you don't have to ask what you're looking at. It's Venus. Short story, I have a kind of relationship with some of the local meteorologists because I have a son who's a weather nut. He's a meteorologist now. So anyway, I conversed with him and I had Leland Statham say, our camera crew took this picture in the morning sky and they want to know what they're looking at. The picture when we blew up, you know, what our camera got, it looks like the moon, but it's way too small. And I said, congratulations. I said, boy, is that. I mean, they were doing this from their helicopter. That is a good camera. I don't want to know what they paid for it. But yeah, they caught Crescent Venus.
But they didn't know what they had.
Right. They did not know because it was just like, why is there this crescent thing that, yeah. So, and of course, there's some nice pairings in the morning sky. So there's the 9th when you can see Antares rising early with Venus, Mercury, and the moon. So that might be, if you don't mind being out really early, maybe the dog needs a walk. That looks like 6:08 a.m. right there. And of course, we have to remember, this is why we're selling solar glasses, because we have an eclipse coming up. Member Mark Manor says he's going to be here at Mazatlan. Not a bad idea. I'm hoping to be somewhere about here, at a little state park. And Dave Quinn over there has got a pavilion reserved in Blanco State Park.
And everybody's invited, right?
Everybody's invited to see me afterwards.
All right. So, and there's a little bit less busy map of the path. Of course, here in Nashville, it will be a really, really, really big total, you know, partial eclipse. But what, you know, and you're going to get it from people. They're going to say, but it's over 95%. Isn't that good enough? And of course, no, it's not. It's the difference between day and night.
Yeah.
And we would talk to a lot of teachers who would say, we know you think we're trying to be overachievers, right? 95 is an A, right? But in this case, it's just not. You have to get in the path.
But it's 95. 95 would be a thin crescent. Like
Yes.
Glasses.
Yes.
You just have a thin crescent.
And that's
Yes.
really when you need the glasses. Most of the time, if you look at the sun, you're not going to damage your eyes because you're not going to stare, right? You're going to get a face full of sun and you're going to look away. When it gets really thin, you could stare. Don't. Okay? Do not stare. Yep. For you, your camera, you know, and everything else. So, yeah. Lots of glasses. There has not yet been an eclipse for which too many glasses were made. So, and you know, if the sunspots are big enough, you can see them through these. So that's another cool use of solar glasses. And Merry Christmas from the James Webb Space Telescope. So many galaxies. All right, I think this is the transition slide. So I didn't get a really good, you're gonna have to introduce yourself, but William Lamb from Vanderbilt is gonna come up and talk to us about some of the really cool stuff that we're doing. Okay, but I'm gonna leave this with you too.
Oh, is it
It
clicker?
does work for the back and forth anyway.
Cool.
Yeah.
I do. All right, great. Yeah, hi everyone. My name is William Lamb. Thanks for having me here. I'm a fourth year graduate student at Vanderbilt University, and I'm a researcher for the NanoGrav experiment. So we had a really exciting year this year for our experiment. We made it onto the front pages of many news sites. So yeah, I've been invited here just to explain some of that research. Also, thanks for the food as well. It's really good.
Just for you.
So just a little bit about me. I'm from a little village called Penny-sod-Wine in Wales in the UK. Technically, it's not a village. It's too small to be a village. It's actually called a hamlet. There's about 100 people there. Surrounded by sheep. We're on the edge of the Urari National Park, which is a dark sky reserve. So I got to see nights like this quite often, and that's what got me into astronomy. I'm also a first language Welsh speaker too, and yeah, it's just the best place to be to learn about astronomy and go hiking at the same time. For college, I went to the University of York in northeast of England, where I learned how to do swing dancing. Is also just a really pretty place to go hiking as well. I'm told that there's really good dark skies over there too. I never got that opportunity, unfortunately, because I didn't have a car over there. But if you get the chance, do go. And now I'm at Vanderbilt University. I started there in August of 2020. Very interesting year. When I'm not working, dancing, it's where I met my partner, Chelsea. Yeah, life is surrounded by cats, and yeah, sometimes I'll get some work done too. So this talk is based on an astrobyte that I'd written. Astrobytes is a collaboration of grad students from across the world, mainly in the US and Europe. Every day we write a small 700-word overview of the latest research papers that have just come out in astrophysics. So if you'd like to learn about the latest research, come check out our website. I'll have a piece coming up there in a few days, but this is my first piece, counting supermassive black hole binaries with, I need to look behind the screen, customers at a coffee shop. So talking about our experiment and how we can learn about black holes with it. So in this talk, I'll go over what supermassive black hole binaries are and what gravitational waves are before going into our experiment, which we call the pulsar timing array, and then why this is important, why we can do what we can do with pulsar timing arrays. So first of all, just like what is gravity? We have this in school, we learn about this Newtonian view, like gravity is a force, masses pull at each other. Not quite true. Einstein showed that gravity is actually a bend in space and bending in space-time. So mass tells space how to curve, and space tells mass how to move. And if you take that bending to its logical extreme, you get a black hole. So it's a region of space where light can't escape. So you have this singularity in the middle that we don't really understand, but you'll have the surface on the outside called the event horizon, and that's the point where nothing can return, essentially. To give you an idea of how big black holes are, if you took our sun and just compressed it all down and turned it into a black hole, the black hole would have a radius of nearly 2 miles. So to give you a comparison of what this looks like, I've put this in the center of Nashville's big black hole, which is the new Titan Stadium that's being built. It pretty much encompasses downtown. But then we can also get these bigger black holes as well. So these are some photos from the Event Horizon telescope that you've probably seen from the past couple of years. On the right, we have Sagittarius A star, which is the black hole at the center of the Milky Way. And so that black hole is just smaller than Mercury's orbit, but it has a mass of 4 million suns. So having that much mass into such a small space is pretty crazy. But then you have M87 star, which is the black hole at the center of galaxy M87, which has a mass of 3.5 billion suns, and it's just a little bit bigger than our solar system. So these things are quite small, but also quite big too, just compared to like the scale of the universe. So what I'm interested in my PhDs are binary black holes, because these take Einstein's theory of general relativity to quite big extremes. And this is where we can start testing where it fails. Because right now, Einstein's general relativity passes every single test, but we know it's not the final theory of the universe. It has to break somewhere, because if you try and combine it with quantum physics, things get a little bit messy. So if we take two of these supermassive and dense objects where things can't escape from and start orbiting around each other, we get some interesting effects, such as gravitational waves. So gravitational waves are these ripples in space that come from really massive objects that just move quickly through the universe. For example, having a binary black hole system that is inspiraling into each other and eventually merging. If you had like a ring of planets and then put a gravitational wave going through into the screen like this is how the wave would distort that ring. And just a quick like physics reminder, like some important things to do with waves. Each of them will have a wavelength, so just like the length between peaks. It'll have an amplitude, so just like how strong it is, and it'll have a frequency, so the amount of wavefronts that come through a region every second. So we believe, so theory of galaxy mergers, or just how galaxies form, is that they form after many, many mergers over the history of the universe. So if they're merging, the black holes at the centers of their galaxies will eventually fall into the middle of the new galaxy, form a binary, and eventually merge. And we see across the universe that there's typically one supermassive black hole at the center of each galaxy. So there must have been these many binaries that have eventually merged. And the way they merge is by giving off these gravitational waves, slowly and spiraling, losing energy, and they'll get close enough to collapse into on each other. So that means there must have been a lot of these binaries across cosmic history giving off gravitational waves. So it's kind of like couples at a cafe just chatting with each other. They're all giving off these sound waves that we could start to measure. So we can learn about these binary black holes by listening to gravitational waves. And there'll be different types of sounds you'd hear at this cafe. For example, you'd have these really loud, short screams, such as from a baby, and that baby's very tired parent. Or you might have some customers there who are there for a very long time, also have very deep voices, for example, and they're a part of the background hum that go on and on and on and on. Gravitational waves are similar. There's a gravitational wave spectrum. So this is a plot of what we expect to be the spectrum. So on the bottom axis is the frequency of gravitational waves, and it goes from a frequency of one wavefront every 10 years up to one wavefront every couple of seconds. Excuse me. And then on the y-axis, we have a way that we describe the power at each frequency. So you've probably heard of the LIGO experiment a couple of years ago. Yes, question.
Can we ask questions during?
Oh yeah, of course, yeah.
But when you say wavefront, you mean peak to peak
Yes,
is 10 years
yes.
on the extreme?
Yeah, so it's a really slow evolving wave. And to give you just an idea of how long that wave is a couple of parsecs. So it's a very, very long wave. So you've probably heard of the LIGO experiment. They were the first to discover gravitational waves. There's one down in Livingston, one in, Livingston, yes, Louisiana, Hanford is in Washington. And there's also other LIGO-like experiments that all work together. One's in Italy and one's in Japan. And they're able to detect these really high frequency gravitational waves from solar mass black holes that merge into each other. So that merger is that little wave signal that you see in that plot. I don't work on these kind of gravitational wave signals, so I won't go more into that. I work more on the low frequency gravitational waves, these gravitational waves that have with a frequency of one every year or one every 10 years. And we're also going down into the one every 15 years now, because that's just how long our experiment's been running for. But these gravitational waves come from inspiraling supermassive black holes. So black hole binaries with masses of about 1 billion suns, slowly orbiting around each other, giving off gravitational waves. And as I was going over before, this is just a result of galaxy mergers. Over time, you'll get a load of these binaries slowly orbiting around each other, giving off gravitational waves. And eventually forming, we believe, one single black hole. But the problem with general relativity is if you assume that only gravitational waves are being given off by these binaries, the amount of time it will take for that binary to merge with each other would be longer than the age of the universe. But we only see these one black holes at the center of galaxies. But general relativity says we expect to see a binary at the center of these galaxies. So something's going wrong there. Something's not quite right in general relativity or our models of galaxy formation. So this is what we want to study using gravitational waves. Like, what is going on here? Yeah, so we see these single black holes at the centers of galaxies, but gravitational waves aren't enough to actually bring them to merger. So what is currently going on? And we can't actually look at the centers of these galaxies either, because they're so far away. Black holes are so small compared to the size of the universe. So using optical telescopes right now is not a way to be able to learn about these things. But one thing that we can do is by listening to these gravitational waves. Essentially what we need are a load of microphones. So I'll just go over now what our microphones are. They're actually pulsars. So pulsars are the step between a star and the black hole. They're extremely dense cores of stars that rotate extremely quickly, and they radiate beams of radio waves from their magnetic poles. And those magnetic poles are slightly off axis from the axis of rotation. So they sweep these radio waves across the sky. And sometimes sometimes those radio waves will come into our line of sight. So as they rotate, you'll get this pulse of radio waves. And the pulsars that we specifically look at, we call them millisecond pulsars because they rotate once every millisecond. So they're rotating 1,000 times per second. So we see these 1,000 pulses every second. So that's why we call them pulsars. So yeah, there are microphones because we can now use them as timekeepers because we know that we should see these pulses extremely regularly because they're so dense and they're so massive. They don't lose time over time. And we can model them extremely well. For a long time, they were actually used as our clocks before atomic clocks came into being, because they're just such reliable timekeepers. So they were first discovered by Justin Bell back in 1960s in Cambridge. This is the pulsar that she discovered. So you see all those pulses. I'm sure you've all seen this plot before though, but in a very different context. Anyone know what it is? Any Joy Division fans? Yeah. So this is the album cover for, is it Unknown Pleasures by Joy Division? You'll see this a lot on t-shirts, especially nowadays as well. But this is a very famous plot. It was actually in someone's PhD thesis. It would be really nice if someone could actually use my PhD thesis as an album cover. So just putting out there if you know any songwriters. So how do we use pulsars to detect gravitational waves? Well, we start measuring all these pulsars in our Milky Way, and a gravitational wave will pass through. And that gravitational wave, because it's stretching, compressing space, it changes the distance between us and the pulsar. That means the times in between pulses from the pulsar will change. So we see this slow moving change in the arrival times of the pulses from the pulsars. To give you just an example of just like how big this difference is. So the pulsars that are a couple of hundreds or thousands of parsecs away, the gravitational wave is about a parsec long. So over those distances, the change in distance would be a few meters between us and the pulsar. So that means the difference in when we'd expect the pulse from the pulsar and when we actually observe it is actually a couple of nanoseconds. So it's really, really small, but because these pulsars are so precise, we can actually detect this, which I'll come to later on. So what is a pulsar timing array? It's just a bunch of pulsars that we time regularly to try and detect these gravitational waves. What we've essentially built is a galaxy-size detector for gravitational waves. So we're seeing all these galaxy mergers going on, all these binary black holes emitting gravitational waves, and they're just bathing our galaxy with gravitational waves, which we detect using this array. So we need a lot of pulsars because let's say if we just measured one pulsar really, really well, how do you know that it's a gravitational wave that's causing that change in distance and not some other observational effect, like some gas passing in between us and the pulsar? So if you take an array of pulsars and start measuring how correlated those changes in the timing response is between those pairs, the correlations on the y-axis, the vertical axis there, and you measure it as a function of the angle in the sky between those pulsars, general relativity would predicts a very specific curve that we call the Hangs and Downs curve, which you see with this curve right here. And it should show the data that the NanoGrav collaboration published this year And as you can see, it is really, really close. But this correlation signal is kind of like when you take two TV antennas. So if you imagine like two old school TVs and put the antennas at the same like orientation as each other and see how well the TVs pick up the signal, and then compare that to each other as you move the TVs at a different angle to each other, the signal would change. Given this, not necessarily this curve, it's a little bit different for electromagnetism, but if you're able to do that with gravitational waves, you should expect this curve, and that's what we're seeing with the NanoGrav experiment. So just a little over, just going over a little bit with our group. We call ourselves VIPER, the Vanderbilt Initiative for Probes into Extreme Relativity. So these are some of our members. I'm one of the grad students in the bottom left right here. And we all work for NanoGrav, the North American Nanohertz Observatory for Gravitational Waves. So we have members across North America. We use radio telescopes formerly we used Arecibo, but I'm sure you've all seen that collapse a few years ago. We use a Green Bank telescope in Virginia, the Very Large Array in New Mexico, and the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, in British Columbia, up in Canada. And this is what our data set looks like. So every vertical line is a different pulsar, and every dot is a different observation of these pulsars. And we've been timing these pulsars for at least 15 years. The 15-year data set contains 16 years of data. Don't ask me why. But we're still observing. So right now we have almost 19 years of data. But we've only analyzed the first 15 years because it takes a little while for our analyses to happen. So yeah, these are our telescopes: Arecibo, Green Bank, CHIME, and the Very Large Array. And we're members of the International Pulsar Timing Array. So it's not just our side doing it. We have the European Pulsar Timing Array that use some radio telescopes up there. We have an emerging PTA in China, so the CPTA. There's the Parkes Pulsar Timing Array down in Australia, the Indian Pulsar Timing Array, and a new pulsar timing array with the Meerkat telescopes down in South Africa as well. Just last week, we all met in Bonn in Germany, so I'm a little bit jet lagged still, but the idea is eventually we're all going to combine all our different data sets together, because everyone has a good data set, but it'd be even better if we can eventually combine them all. But yeah, in June, we released our results showing that we have really strong evidence for these gravitational waves at low frequencies using NanoGrav, the EPTA, the PPTA, and CPTA experiments as well. We're all seeing the same signal, that same Hellings-Downs curve, which shows that there is a gravitational wave signal coming through our pulsar timing array. Our experiment is actually working, which is hugely exciting because we now have the biggest gravitational wave detector that anyone's ever built. We haven't built it, but kind of we had. It's a really weird way to say things. But yeah, we had a really cool event in the National Science Foundation's headquarters in Washington, DC. So that's my advisor, Steve, the chair of NanoGrav, speaking next to Kip Thorne. That's Jocelyn Bell Burnell down there, who joined us on video link, seeing how her discovery has led to this really cool detection of gravitational waves. We made it onto the front pages of different newspapers and media sources, and I made it onto the front page of the Welsh language BBC news service, which is pretty fun. So why is detecting gravitational waves with pulsar timing arrays really important? So as I went over before, general relativity and quantum physics don't quite mix. So one of those two theories is, or one of the two, or either both, aren't quite accurate. So we would like to break general relativity and see which insights we can find, like what can we find is wrong with it. If there was something wrong with general relativity, that curve that I showed you earlier would be slightly different, and we should be able to detect that using this experiment. We have a new messenger for the universe. So a messenger is like something that sends information. So in the universe, in astronomy so far, we've just had light, but now we have gravitational waves. And if we can measure gravitational waves from a specific galaxy and also observe it, we have two different ways of measuring it. So we'd learn a lot about galaxies from that. These gravitational waves could also come from what we call new physics. So alternative physics theories that have no other ways of being tested, but we could test them using pulsar timing arrays. And you won't need to have like really big machines to do this, like the Large Hadron Collider. We just need a bunch of radio telescopes, which are relatively cheap. We're developing and training new students in data science, and they'll either stay in academia and create new things, or they'll go out into industry and build some really cool things that people can use as well. It's really cool. We've built a galaxy-sized detector. It's amazing. But the most important thing for me is this final parsec problem. So is general relativity broken? Will these black holes forever stay as a binary, or will they eventually merge within the age of the universe, as we actually observe from observations of galaxies? So how do we count these binary black holes using our data? So as I was going over earlier on, when a gravitational wave passes through our detector, it changes the distance between us and the pulsars. So we see a difference in this timing response, and it will meander away in a rather random way. So this is just showing how if there was no gravitational waves, our timing response for these pulsars would just stay constant. It would just be these gray lines on the screen. But because there are gravitational waves there, we see them meandering around this gray line. Some of them, yes?
So you're just measuring the phase of the gravitational wave against some high reliability standard. You can see the phase of that wave shift.
So we don't quite see the phase because we actually see multiple gravitational waves at the same time. So it's really difficult to actually tease the phase information out at the moment. So we hope to be able to do that in the future. So yeah, because there are multiple gravitational waves in the detector at the same time, it's not just like one sinusoid in our detector. We actually just see this combination of sinusoids that is causing this random walk over time. So this is what we then compare against each other to get this correlation to calculate the Hans-Nernst curve. But we want to be able to see these sinusoids from each of these individual binary black holes. And the way we can do that is using something we call Fourier decomposition or Fourier analysis. So we take this very complicated signal and we just turn it into a series of sinusoidal waves. And this is actually how we listen to music nowadays. I did have a different slide for that. But yeah, if you want to turn sound into like a digital signal, you just turn it into these bunch of sinusoids. You say how much strength is in each of these frequencies, and then you combine them all together at the other end, and that's how we listen to music nowadays. So we can see these different strengths of gravitational waves at each of these frequencies.
But you're trying to do the opposite, right? You're taking the signal you have and wanting to break it down into the, into the different sinusoids.
That is exactly what, And then we get a spectrum that looks like this. So it says at each frequency, how much power is there, or what is the volume at each of these frequencies? And yeah, that was the slide I thought was going to come up. I think some of the animations slightly mixed around when I was transferring all of these slides over. But yeah, this is how music is, or my voice is coming through on Zoom. It's being decomposed into these Fourier modes, being transported through the internet as like these different volumes at different frequencies, and then being combined all together at the other end. But if you decompose my voice into, or if everyone started chatting with each other, and we decompose them using Fourier analysis, this is the kind of spectrum that you'd might expect to see. So maybe like a load of loud voices at lower frequencies and a few high voices at higher frequencies. But the reason we call this specific kind of signal red noise is because if you took light from if you took red light and then you did this Fourier analysis on it, you'd see a lot of frequencies, a lot of power at these lower frequencies, these red frequencies, and few frequencies at, very few power at higher frequencies. So you'd get this slope that looks like this. So it decreases as it increases in frequency, and that's why you'd see red light, and that's why we call this red noise. If anyone is wondering where this terminology came from, white noise, the power at all frequencies are about the same, because white light is just a combination of all frequencies of light are about the same power. So yeah, just a little bit of trivia there for you. So the power spectrum that we're seeing is a red noise signal, because we're seeing a lot of power at low frequencies and less power at high frequencies. So what does this mean for our black holes? What kind of, like, what are the black holes doing to cause this kind of signal? So when the black holes are kind of far away from each other, they release low frequency gravitational waves, and the power of those gravitational waves is actually quite small. They're just very faint whispers. But because the power is very small, it takes a long time for them to start getting closer to each other. So as they get closer to each other, the frequency of the gravitational waves that they emit increase. But because it takes a while for those weak gravitational waves to cause the black holes to move closer to each other, we actually see a lot of black holes at these lower frequencies. So because there's a lot of black holes all whispering, it actually creates this really loud signal in our detector. So that's why there's a lot of power at the left side at the low frequency of gravitational waves. When the black holes are closer to each other, the strength of the gravitational waves that they emit are actually really, really strong. But because they're strong, they lose energy faster. So they move out of this frequency range much faster. So there's less black holes at those frequency ranges. So you have very few, very loud voices. So it actually looks kind of quiet in our detector. So yeah, that was what we predicted by the black line. And we're kind of seeing it in our data from that blue line. They almost look similar. It's actually a little bit more complicated than that, though. If we take a load of simulations of our universe and included some other interactions that are going on between the black hole binaries and its host galaxies, we'd get all kinds of different shaped spectra like this. So I was showing you one that looks like a straight line. It's actually a little more curved because the black hole is also interacting with its galaxies. And that's a really important difference right there. Because it's interacting with its host galaxies, the black holes are actually losing energy a lot faster. So the binary is being driven towards merger a lot faster. And this is what we saw with our data set. Because the galaxy is interacting with the binary, causing that merger to happen faster, it means that general relativity is saved those binaries are able to merge within the age of the universe. So we were able to look at what kinds of masses of binaries that were creating these gravitational waves and what kinds of separations were going on between the binaries themselves. And we're seeing that these black holes must have small enough binary separations such that they'll eventually merge within the age of the universe. And what this actually means for our cafe is that there are a lot of very hungry weightlifters all sitting at the tables with each other. And eventually they'll all go home with each other. This is not the end of the story though, because there are actually a lot of things in our data set so far that we don't quite understand. We can't actually conclude that our experiment is proving that these binaries must merge and that general relativity is safe yet, because there are other measurements in there that we haven't quite done or things that we haven't modeled quite correctly yet. So, for example, if you've been to a cafe and the people at the table next to you are extremely loud, you just hear that one voice, like they kind of overwhelm your senses, right? That could be happening with us as well. There could be a really close source of gravitational waves from a local galaxy that is actually overwhelming our detector, and we want a specific frequency. So we want to be able to see if we can find them, because that would be really interesting, because you could also point a telescope at them and start observing them with the gravitational waves and using optical telescopes. But this is really annoying for me because it actually throws off our measurements. So we want to be able to model that away. Have you ever been to a cafe before and like someone drops a plate and like the atmosphere completely changes? That might actually be a source of gravitational waves for us, but a slightly different way. So at the beginning of the universe, just after the Big Bang, things were very, very hot. And the universe was in a different phase. Talking about phase as in like solids, liquids, gases. The forces in the universe at one point were all combined with each other. And below a certain temperature, they would split up, causing this phase transition. It's kind of like a liquid freezing into a solid. And that would give off gravitational waves, which we might be able to detect using our detector as well. There might be other weird stuff going on, like other sources of gravitational waves that theory predicts that has not been tested yet before. So you might get these unusual characters in there that we could also measure, which would be pretty cool. So you have all these combinations of gravitational wave sources going on that could be adding to a signal, and we want to be able to disentangle them out. But there's also a lot of noise that we haven't measured yet. So it's kind of like if you had these microphones in your cafe and you have all these background sounds that have always been there, like people making the coffee, and you haven't accounted for that, then that will also throw a few measurements. So there are some pulsars out there that we are not modeling very well at the moment, and we're improving those measurements, but they're causing some weird features in our data sets as well that we're currently working on to make these precise measurements. So we can disentangle all these different sources of gravitational waves from our data set, and especially to be able to look into this astrophysics problem of black holes merging in galaxies. So the future of pulsar timing arrays will be detecting these single sources of gravitational waves as well. They're both a problem and something really cool that we can do. And we want to collaborate with these different traditional telescopes across the world to be able to observe these galaxies that be emitting these gravitational waves that we can see. Yeah, more noise analyses and use more complex models of pulsars and gravitational waves to be able to make our measurements more precise. So we can finally interpret what is creating this background of gravitational waves that we're seeing in the signal. So the way we're doing this right now is using a lot of high performance computers, these really fast supercomputers across the world. We have one at Vanderbilt, and each of these analyses takes a couple of days or weeks per analysis. As we're increasing the size of a data set, these analyses take even longer and longer and longer. It's not sustainable at all, because if we want to be doing this really cool science, we need a much faster way of doing this. Ideally, we would like to do it on a laptop in a couple of minutes. And that is actually what I'm doing for my PhD. I've developed a piece of software that allows people to be able to fit them chosen models to a representation of pulsar timing array data sets really, really quickly. These little contours right here is actually the real NanoGrav 12.5-year data set. So the orange contour is the way that takes a couple of days to a couple of weeks. And the blue and the green contours are two different ways I can do this on my laptop in less than 5 minutes. So yeah, the orange one I want to say it took about 2 weeks to get. And they agree with each other completely, almost completely. So we can start doing this really cool analyses using my methods. So anyone can start counting black holes in a coffee shop. So thank you for listening. Any questions?
So let's describe the pulsar array as picking up this hum going on gravitational waves. Now, in the 15 years that you've been listening, is the hum itself kind of like constant, or are you seeing mergers of black holes in that time space?
So we will, at this frequency range, we won't see mergers going on. That would happen at slightly higher frequencies that we can't probe using our experiments. We assume this background to be stationary over the time span of a data set. This could change in the future though, because these binary black holes are creating gravitational waves, they're slowly merging towards each other. They won't merge, but they're merging towards each other. So that means the frequency of gravitational waves they're creating will be changing over time. So you would see this difference over a period of thousands of years. But in the 15 years we've done this analysis for, that change is completely negligible. It's a really good question. It's might be an issue in the future, and it's something that other experiments think is a problem. We don't think it's a problem with ours at the moment.
There's a research thing that came out the other day comparing black holes with holograms. Did you see that?
No, but I've heard about this holographic principle before. Are you just asking like what it is, or
Is there any work going on there?
with us? No.
No, I mean,
No. With pulsar timing arrays as well, no, I don't think we'd be able to. I don't think we'd predict any gravitational waves being emitted from them, and it's not something that we'd be able to measure using our experiment. I think the idea is you can explain everything about the universe on the surface of the black hole, and I don't know how you'd be able to experimentally verify that. It's just a really neat trick of maths that comes out from theoretical physics, but whether you'd be able to test that, I don't know.
I'm still trying to picture exactly what a vibration in space-time is, but if you have a binary black holes over here, and they're at some particular grid point in space-time, and we're at some grid point space-time, then as space-time wiggles, our coordinate points aren't changing, so it seems like really the distance hasn't changed, but when we get these variations in pulsar energy, how do we know that's maybe distance changing or maybe we're experiencing a different time?
Yeah, so this is the complicated thing with general relativity is it's all about frames of reference and whose frames of reference we're talking about. So from the frame of reference of us on the Earth, we assume to be stationary, and we're observing these pulsars. As a gravitational wave is passing through, you would see this change in distance from the light that is being emitted from the pulsar to us. So that because the light had to take a little bit longer or a little bit shorter from the pulsar to us, we say that that is a change in distance. And it would be the same thing with the binary black holes even further away as well. There would just be this small change in distance.
Changing this, even though our points on the space-time grid are essentially the same.
Yeah, yeah. It's a really hard thing to visualize. It's the same with this idea that the universe is also expanding. If you use this frame of reference of what we call conformal space-time, like or co-moving space-time, nothing is actually expanding. But that's just the way that we're measuring this change in distance. But if we're looking at it at kind of like an absolute frame of reference where we're using light to start measuring things, then you'd see this expansion. Yes.
So LIGO, they're looking at high frequency events and then also time varying events. And so they're able to localize the source in some direction. Are you able to?
Yeah.
say a wave is coming from a particular direction?
So the way that LIGO is able to localize these gravitational wave mergers is because they have multiple detectors on Earth. So it's not just LIGO's Virgo in Italy and Cagra as well. So you have these 4 different detectors all detecting this gravitational wave event. But because gravitational waves are traveling at the speed of light, there'd be a slight difference in when they observe this event. And like the difference is on the order of nanoseconds or milliseconds, depending on which direction the gravitational wave's coming from. So you have this triangulation in the sky. It's like, okay, this gravitational wave came from this direction. And then you might look at like which galaxy or which cluster of stars that region contains, and then start pointing telescopes at it. And that's how they're able to make this first, what do we call it? Multi-messenger astronomy detection. So they're able to see gravitational waves and observational light from this event. We can theoretically will be able to do this once we get better measurements of this gravitational wave background. You'd be able to, because we have these pulsars scattered across the galaxy, so you have a lot of these microphones in different locations. If there are more gravitational waves coming from one region of the sky compared to the other, one region of the sky would have a stronger response compared to the other. That would also help this black hole problem as well, because there are only a finite number of binary black holes in the night sky. So you'd expect these gravitational waves to come from these very specific sources in the sky. If the majority of the gravitational waves is actually coming from something from, say, the Big Bang, they would actually, the gravitational waves coming from that would come from all directions equally. So you would actually not see any differences in the strength of gravitational waves coming from any single direction. So yeah, that localization problem is a really important thing for our experiment as well. But because we have these different pulsars in different places in the sky, that's how we'd be able to try and tease this out.
When you in the Fourier analysis, I mean, you have wavelengths that are like reliable, like they're your friends, you know he's out there, this particular frequency is there and shows up all the time. You have a catalog of those or a list, or how many have you identified?
We've not identified any yet. That is a problem that one of the grad students in our department, Paulina, is working on.
And when you're showing the graph of trying to pull out those individual signals, the graph was 3.
Yeah.
But if there are thousands or millions,
Universe is big.
yeah, it's gonna be tough.
Like, we're not going to be able to tease out all of them. There's always going to be like a background hum that we're never going to be able to resolve, but we'll be able to hopefully resolve on the orders of tens or maybe hundreds of them in the future.
And those being either closer ones or
Probably
massive.
closer ones, yeah. Closer and really strong ones, yeah.
So it sounds like a lot of the work's being done by students. So what happens is they graduate, and what will happen? Will you try to continue this work?
So yeah, I'm hoping to continue into a postdoc, and I'll continue working on either NanoGrav or a different international pulsar timing array group with the same research though, because we're all using the same techniques and we're all helping each other out with this experiment. Yeah, the question on like what different students will do in the future is a big one. Yeah, the idea of their theses will be to develop new methods and new techniques so we can learn more. And hopefully that would be like a contained project. So if they decide to move out of academia, we'll just use their methods still, or someone could take up their research. Like a new grad student will always come through and they can take that research into the future. But to give you an example, 2 weeks ago, I was in Hanover in Germany visiting one of my colleagues. He did his PhD and a postdoc on pulsar timing arrays like 10 years ago. So when this entire field was just beginning, didn't know if it was even going to work, but he worked on a lot of the data science for it. Then he had enough and moved to Microsoft. And then he had enough of Microsoft and moved back into academia. And he's taken up this research again. But these methods I've been developing, he originally proposed them in 2014, and no one had actually worked on it until I took it up 6 years later. Yes.
Who's funding this? What agencies, like internationally or in the US?
So for NanoGrav, we're funded by the National Science Foundation, so the taxpayer, thank you all very much. And also the Moore Foundation as well. I don't really know much about the Moore Foundation, but I think they're like a private group.
Was it Gordon Moore Foundation?
Yeah.
Right, it was Intel, right?
Yeah, that's true. Yeah, Moore's Law, right? Yeah. For the European pulsar timing array, I think they're funded by the EU, the European Union, but I'm not sure. The Parkes pulsar timing array is by CSIRO, which is the Australian Science Foundation. The Chinese pulsar timing array, I believe, is fully funded by the Chinese government. I'm not sure with the Meerkat or the Indian pulsar timing arrays, though, but it's mostly taxpayer funded.
What's kind of the budgets of these agencies?
So for NanoGrav, when we got our last grant, I think we were given like $5 million either every year or for the 5 years. I don't remember. There's on order of a couple of million.
So there's maybe like 50 groups doing this kind of stuff worldwide?
Like different pulsar timing arrays.
Yeah.
Right now there are 6.
So
yeah,
it's like a $20 million a year.
Yeah, pretty much.
And you've got like an impressive body of work here that you've collected up, and you're wrapping up and you're about to defend your dissertation. And...
I'll be defending either summer 2025 or summer 2026. So I still got some time. Yeah. So I want to use these methods I've been developing and actually use them to try and see what we can actually start learning. Like if I apply these methods to actual data, what can we start learning about either black holes or these Big Bang kind of signals as well, and how we'd be able to tease out all these different signals.
For like 18 months from now, we can ask for an update.
Yes. More than welcome to. By then, we're hopefully going to have the International Pulsar Timing Array data set out. So taking the NanoGrav, the European Pulsar Timing Array, the PPTA, and the Indian Pulsar Timing Array. Oh, and also Meerkat. So 5 out of the 6 PTAs, and just mesh them all together into one super data set. So the reason we haven't done that so far is because like restrictions with our funding agency, so we have to do this all individually. But that was a good thing because we're all independent and we're all confirming that we're all seeing the same thing. But if we then combine it into one super data set, we'd actually be able to get a better measurement on that curve, have more evidence for the gravitational waves, and theoretically have a better measurement on the power spectrum for the gravitational waves as well. So we'd be able to tease out these different signals a lot better too. But yeah, to give you an example, like NanoGrav has 67 pulsars, but if we compared them, if we combined all those different data sets, we then have 115 individual pulsars. And like, because we're in North America, we only see a certain section of the sky throughout the year. Having radio telescopes from across the world in one super data set, you have these 115 pulsars in all directions of the sky. So it makes our detector significantly better.
You mentioned that on one of your slides about the vibrations in space-time being a messaging. We have light waves, and now this is another messaging. But maybe you said this, but I missed it. Is there some wonder about movements in space-time traveling? It's faster than the speed of light. Like soon after the Big Bang, you know how apparently I think the theory is that there's enormous expansion. So can you speak to that?
Yeah, so that would be inflation. So the universe expanded from this tiny little speck into this huge size in like fractions of a second. It's something that I don't fully understand, but I'm still working on trying to understand. But the speed of that expansion would generate a particular spectrum of these gravitational waves that we should be able to detect with this experiment. So you'd have, instead of the straight line, you would have this different shape. If we can tease that out, we'd be able to learn a lot more about the first fractions of a second before the Big Bang, which would be really cool because right now there are no other ways to be able to detect that, but we can with this detector. And the reason for that is we can only see light in the universe from up to 380,000 years after the Big Bang happened, because the universe is a lot smaller, it was a lot hotter, so everything was a plasma, which means the universe was opaque. So yeah, all the gas was separated into electrons and protons. There was a lot of electric charges, so the light was just being scattered in every direction. So it'd be like a fog between us and the door. You just wouldn't be able to see anything. But once the universe cooled down enough, everything, like the protons and electrons combined together into atoms, and then light was able to pass through freely. So that happened 380,000 years after the Big Bang. So that would be the first light you could actually detect from, say, a galaxy or something. So you've all seen the cosmic microwave background. It's like this little mottled diagram, little mottled figure. That surface of recombination 380,000 years after the Big Bang. It's the earliest light that you could see. But gravitational waves, because it doesn't interact with other, like say it doesn't interact with matter very strongly, it can pass through the universe without being affected by, say, electric charges or something. So those gravitational waves from the beginning of the universe has traveled to us completely unimpeded. So that's why we think we could be able to detect these gravitational waves from the beginning of the universe. It's been traveling for like 13.8 billion years completely unimpeded. So it's a messenger from that time.
Any other questions? Let's see. All right, so the usual sorts of things, make sure you take the food. It was great. Thank you to everybody who brought food. And we'll see you next month at dinner.
Merry Christmas,
We're gonna give her right now.
What about the?
Oh, yeah, what about that?
Oh, the auction, you haven't bid, go bid. If you, let's see, anybody want a few more minutes? If nobody has any more bidding to do, then take it or something.
I don't see any bids.
Yeah, he said, sorry, she is, 1:27 a.m. Well, it's Hannah's driving, it's going down.
Oh. She's fast, huh?
I would stop it. Yeah, we can stop at Morristown. It's still 4 hours. I would. Where we're gonna be at for the 8th. Yeah, start Monday. We're going somewhere. Hey, well, yeah. I'll do that.
The sky is supposed to be clear.
While
It's all these this week and donate to the.
scale is like
Well, we're staying. in the same
So,
time.
But
Instead of paying $150.
So it wouldn't have to run on the
my negligible pet to dig out. So what you can get to do, is see
Not stay there, but it's not dark sky. I think it was.
So the frequency
You gotta watch
just
it all works.
so that say like
Right now, I did.
I always.
Take care. And that's a bottom. This is very. Relevant for 718.
Yeah, it has a cool mix of all.
Meaning the color curve. Yeah, okay. Good. You got my email, you know.
But then as they go through the, that will end up taking almost any form when we. But I'm finding my time to not. Okay, I guess we'll do it.
Not being great yet.
I'm not trying to, study value of software.
I know it's fun for us.
Theo? Theo?
Oh, that's Joe. I need to cut that off, don't
So we know that there's.
I? Hey, Joe.
Hey, Theo.
Oh, it's-
That worked out very well.
well, good.
So we can actually measure.
I hope you enjoyed that.
I did. I would have enjoyed it better if I had my hearing aids fixed, but since you recorded it, I would like to get it later on and go through and borrow the recording of it and
Okay.
get my new hearing aids whenever they get. I'm on my third pair now in the last 6 weeks. I'm getting them from the VA, and they get them, and they said, "Well, they don't work."
But yep.
But I appreciate you having it on tonight, and I've enjoyed it.
All right, Joe.
Okay.
We will.
All right. Thank you so much.
Okie doke. Bye-bye.
Hey.
Yeah, I think.